All right, we're going to go ahead and get started. First up, we have Segment giving a talk about using containers and using step functions, and Michael Fischer will be dropping some knowledge. So take it away.
Hi, everyone. Testing 1, 2, 3. Okay, I think we got that. Hi, everyone. My name is Michael Fischer. I am the lead site reliability engineer at Segment. Segment is a startup here, primarily located here in San Francisco. We have a little over 250 employees. We provide analytics and event management, event processing, and warehousing for all sorts of web companies, from small startups to very large enterprises. I'm here to talk today about some of the work we've been doing with EC2 Autoscaling, ECS, and step functions for managing fairly complex container orchestration workloads. How many of you, just show of hands, how many of you are currently using EC2 Autoscaling? How many of you are currently ECS users, running Docker containers on ECS clusters? Okay, cool. How many of you have heard of step functions? How many of you use step functions? That's not surprising. Step functions are one of the lesser known products in AWS, which we think is extremely powerful. And I'm going to talk about some of the cool stuff that it can enable in orchestrating container workloads for complex systems. A little bit of Mojibake there. Sorry about that. It looked better on my Mac, but Segment loves ECS. We're huge users of ECS. How big? As of last week, this was our container workload graph. As you can see here, we regularly run over 10,000 ECS tasks. This is in production, by the way. At any given time, sometimes that number goes up and down with autoscaling, but we run very, very large container workloads on ECS. It's Segment Engineering. Why do we do this? First, Segment Engineering loves containers. Containers are a great way for developers to build software to deployment. As those of you who use containers know, there are no issues with dependencies. Your root file system is completely contained. You don't have to worry about packaging conflicts, library conflicts. You can make the containers as small as is necessary to enable the software. It gives you a very small security surface a smaller security surface to attack, and it allows rapid iteration and continuous integration. Segment is a big fan of AWS. We've been using AWS for many years. We have many instances in production. We use many of the data services there, and we find that ECS integrates very, very well with other AWS components in their portfolio. So EC2, for example, elastic load balancing, autoscaling, ECR, which is the private image registry or container registry, and CloudWatch logs. So if you're not already using ECS, ECS is a container management system that's used to handle deployments of both tasks and services. It's a great fit. When most people talk about container deployment on ECS, the most common use case is for so-called stateless services. Stateless services are, as the name would suggest, services that don't store state. So think microservices that process data in some way, but rely on some other service to actually provide storage. So this is a pretty typical architecture decision. AWS provides great storage services like RDS, DynamoDB, S3, Elasticache, and so forth. These are tasks that can be generally terminated at will. So when the scheduler decides that, pursuant to an autoscaling rule or deployment, that it needs to terminate a task, it's just going to do it without any user input. And typically your services need to be built such that they can tolerate that. They're typically routed to by a load balancer or service mesh. Many of you working with Kubernetes may have heard of Istio. These are basically reverse proxies that perform health checks against your containerized services and will automatically reroute connections to the instances of those containerized services that happen to be up. This is in accordance with the containerized, highly scalable metaphor of cattle as opposed to pets, right? In this world, all of your servers are roughly interchangeable. You have a very uniform collection of anonymous systems on which these containers run. And as long as there's enough resources in terms of CPU, I/O, network, etc., they're all interchangeable for the purpose of running services. The service or routing mesh handles the actual direction of traffic to the right EC2 instances. In some ways, though, Segment is a little bit different. So we like to run as much as we can in ECS. Why? ECS gives us as close to a sort of single pane of glass for managing all of our tasks and services as we can get without writing a lot of custom orchestration code and UIs. Since our developers love to work with Docker, it provides us a natively supported method for deploying those tasks onto our EC2 instances and then managing those life cycles. So what this means, this actually means doing a little bit more than simply our stateless services. We actually run stateful services on top of ECS2. These include Kafka. For those of you not familiar with Kafka, Kafka is a scalable, highly performant, log-based message broker. Imagine a cluster of services that read data off the network, append it to a bunch of files, and then clients that basically tail-f that file, that collection of files. That is essentially what Kafka is. Zookeeper, which is a state coordination system and metadata directory that's used by Kafka, we run that with ECS. Console, it's a key value store, a service discovery solution, and a distributed lock manager all in one. It's a truly fantastic product. NSQD is a message queuing system written in Go. We used it before Kafka. It still provides, we still have a bit of legacy NSQD in our architecture, but we run that as well statefully. And then we have an event deduplicator that we call dedupe, which is a custom service written in Go that uses RocksDB underneath in order to store state. So, but stateful services require a little bit more TLC than stateless services. So suppose that you're doing a scale-in event. Your stateful service isn't being used as much anymore, and you can migrate some of that data, or you can reduce the number of read replicas for that particular stateful service. Perhaps you might want local queues to drain, work queues to drain. Suppose the queues are stored locally on that system. They have some work to do, and we don't want those to drain before signing the instance off. We want a task itself to sign off and preserve quorum, or we want to ensure a replacement task is standing by on another instance. For example, suppose the instance you're running is about to undergo maintenance, scheduled or unscheduled maintenance. You might want to make sure that the work can be transitioned off to another worker before shutting that instance down. I should make a footnote here, is that this is really best effort, right? We don't, Segment and other doesn't really encourage, and I certainly don't encourage, intentionally creating services that work this way if they're going to run them in containerized workloads with a scheduler like ECS. But it is one of those things that sometimes you have to do, if you're running legacy systems, or for example, if that hacked up MVP that you hastily written during a caffeine-fueled binge over a weekend happens to still serve live traffic to this day. Not that we actually do any of those things. But they may not be super tolerant of uncontrolled shutdown, and so they need to be carefully managed and quiesced instead of just having an outside scheduler pull the plug without warning. So how do we handle this? We take advantage of some technologies and some features that AWS provides in its autoscaler. So this is a very useful feature, and I believe, as far as I know, it's still exclusive to EC2's autoscaler. So this is a typical instance draining chart, it's an instance lifetime state machine for an EC2 autoscaling instance. Raise your hand if you've seen this before, like in the documentation. This is actually an incredible useful thing to study in the EC2 autoscaling documentation. So one of the really cool things you can do with EC2 autoscaling groups is you can specify a termination lifecycle hook. And what a termination lifecycle hook does is you just configure this when you set up the autoscaling group, and you give it a name. It doesn't matter what the name is. And what will happen is when the autoscaling prepares to terminate the instance, it will put the instance into a state called terminating wait. And what that does is once it transitions into that state, the instance is still alive, doing whatever is currently running on it. But the autoscaler is now waiting for an API invocation that says, okay, you can now continue with termination. That's called a completion. And so what we do, so what will happen is termination will be deferred until we complete the lifecycle action with a continue signal. And we declare these termination lifecycle hooks on most of our autoscaling groups at Segment. So once we've configured that hook, the hook itself lasts for the lifetime of the autoscaling group unless you modify or destroy the autoscaling group. So one of the things that we've done, so what happens next is when the autoscaler is preparing to terminate an instance, you can configure a CloudWatch event pattern match. So CloudWatch can be configured to, for example, dispatch to SNS, but what we have it do is we have it invoke a Lambda function. So what happens is there's this pattern match here under CloudWatch events. The source is AWS Autoscaling, the detail type, and these are fixed strings, by the way. And we match these event patterns, and then we include the autoscaling group of the group that we want to match. Or you could have no match at all if you wanted to match any of them. So what happens is the CloudWatch event is received, it's matched by the rules engine, and then we have a start ECS drain Lambda function that is invoked when that event is seen by CloudWatch events. And that then in turn invokes our ECS drainer step function. By the way, it used to be, those of you who've been using autoscaling groups for a long time may know about, before what you could do is you could configure an SNS topic to deliver deliver notifications to. That is now legacy behavior. You can still do it, but using CloudWatch event pattern matches is now recommended instead. So, okay, what's a step function? To make a long story short, a step function is a state machine. Raise your hand if you know what a state machine is. Okay, so the state machine is a graph of steps with start, intermediate, and terminating nodes. I'll give an example of this a little bit later. Each step can be one of the following. It can be a Lambda or remote function invocation. It can be a choice, which is basically a branch, a wait state, which is a sleep, a pass state, which can modify the actual state object without invoking a function, or a terminate state. And terminate states can be either succeed or fail. Each step in the process accepts and emits a state object, which is basically, for all intents and purposes, JSON. Looping is okay, which is, when you combine loops and wait states, makes step functions extremely powerful. And the plumbing is included, and it's really inexpensive to operate. I looked at the pricing. 4,000 straight transitions are free per month, and it is 2.5 cents per 1,000 state transitions thereafter. And it does not include Lambda pricing or data transfer fees. Here's an example of what a step function looks like. So these are two nodes in the step functions graph. So one is called get task count. You can see here that it has a type of task. So remember, there's task, choice, wait, terminate, and then the resource is the ARN of the Lambda function we're going to call. And then step functions also provide for retries and exception handling, so you can declare a catch as well if it fails. So we will retry with an exponential backoff if some sort of error has occurred. And then next is the vertex, basically, between or the link to the next step in the step function. So eval task count is the next node or edge, if you prefer, in the step function graph. So eval task count, that has a type of choice, so that's a branch. And then there's a default choice if none of the choices in the list matches. So the default node is called check elapsed time. And then the choice is we are trying to match whether a variable called running task count is equal to 0, and if that is true, then jump to the finished termination task. And each of the variables, when you're evaluating branches or choice types, what you're doing is you're evaluating against a so-called JSON path expression. So in this case, this expression would match $, basically means the root node of the JSON tree. In this case, we're just matching whether or not the running task count as a root object is equal to 0. So here's an example of what a relatively simple instance draining step function looks like. I'm going to walk you through a little bit. So at the start node is drain instance. So what drain instance is it's a Lambda function that through the ECS API tells the instance that's being terminated to go into draining state. And draining state in ECS means don't accept any more tasks, and if possible, if it's a service as opposed to a task, that any service associated tasks on that instance, ECS will try to migrate over to other instances and then terminate it after it's successfully migrated to another instance. Get task count gets the queries the ECS API for the number of remaining tasks on that instance. And then the next step is to invoke a choice called eval task count. And as you saw on the previous page, if it's equal to 0, then we're going to go to finish termination, which starts the termination process over here on that instance. Otherwise, we're going to check the elapsed time, the time since we started the process, the step function, because we record that in the state that we're passing around. And if the elapsed time is below our threshold, we just sleep, which is a wait state, sleep and then retry. It waits, then goes back to eval task count. If the elapsed time has been too long, we notify in Slack. We have a Slack notifier that an unacceptable delay has occurred. We also notify in Datadog as well. And then if it's been too long, we also have a predicate called should terminate after deadline. If that's set to true, then we'll go ahead and finish the termination because we gave up. Otherwise, we'll retry and go wait again. It looks complicated, but one of the greatest things about it is that state functions, if we didn't have, for example, a timeout here, we could run this for a year. And it would wait as long as it takes for the eval task count predicate to match 0. You don't pay for wait states in step functions. And so what this allows you to do is, the big learning here is that you can run very complex systems in Lambda without actually paying for Lambda runtime costs that are spent waiting around. So the maximum runtime on a Lambda, I think, is now 1 minute or 5 minutes. It's pretty high, but you're actually paying, if you're not actually doing real work in that Lambda function, you're just paying it for it to wait around. Well, why should you do that when you get wait states for free with step functions? Another case of using step functions for fairly complex tasks is to update an autoscaling group. What we mean by updating an autoscaling group here in this context is actually to update its AMI, its Amazon Machine Image. Raise your hand if you have to do this task periodically. So there's a canonical method that a lot of people call blue-green. So in the blue-green canonical method, suppose that you already have an autoscaling group with a particular AMI. It's humming along, it's working great. And then you need to replace that AMI on that cluster. So with the canonical method, which is recommended by just about everybody, you create a new autoscaling group with the new AMI. You add the new targets for that new autoscaling group to your existing load balancer. You drain the connections from the old autoscaling group targets, and then you destroy the old autoscaling group. Makes sense, right? It's very straightforward, very simple. It's not a perfect fit for all cases, though. It can be somewhat difficult to orchestrate depending on what kind of orchestration system you use. So if you're using CloudFormation or Terraform, that means you have to have multiple stacks or multiple autoscaling groups pre-declared in advance. And then you need some sort of external orchestration to manage this blue-green deployment. And it can be error prone if you're not careful. I mean, imagine the worst case scenario where you bring down the live stack before bringing up the new one. That would be disastrous. Another challenge is that depending on how you've set up autoscaling, if you immediately add all of your new instances to your autoscaling group, half of your traffic could start flowing to cold cache instances and impact your SLA and impact your response metrics to your customers. It could be extremely costly if you have very, very large autoscaling groups. At Segment, we often run with autoscaling groups 200, 300, 500 instances in size, and we run them on very large C5 9x large instances. So time that we spend doing this transition, we could run into instance resource limits. It could be very costly. And then it's also not appropriate for stateful services, as I talked about before. So to answer this problem, we've had many attempts at engineering for this particular problem, and the one that we're currently experimenting with in development at Segment is called Rollerbot. So Rollerbot, we call it Rollerbot because the interface for it is a Slack bot, but it's, as I said, it's still very much in development, and we're still working the kinks out. Instead of having multiple autoscaling groups, you just have one autoscaling group. And so the basic method of operation is that it updates the launch configuration with the new AMI that's associated with your existing autoscaling group. And when you do that, any new instances that are launched as part of a scale out get the new launch configuration automatically associated with it. So we update the launch configuration, and while there are existing old instances of the previous launch configuration still alive, what Rollerbot does is it adds a fraction of new instances to the autoscaling group by simply increasing the desired count by, suppose it's a 100 instance cluster, we add 10 new, we raise desired count by 10 to bring it up to, say, 110. We wait for them, and we wait for all of their launch hooks to complete. And then we wait, and basically we wait for those new instances to transition to in-service state. Once they're in service and verified, we drain and then we pick 10 of the old instances and we just terminate them. And we decrease, and every time we terminate, we decrease the desired count until it reaches back down to the original count again. So if we were at 110, we then go back down to 100. And we repeat this process over and over until there are no old instances left. And then we also have a stateful method as well that's useful for replicated data services like Kafka that simply go one instance at a time, drain and terminate one instance, and then add a replacement until that replacement instance is quiesced, so that we don't end up having desynchronization of our replicas. So I had to, in order to make this all fit on the screen, I had to decrease the font size a lot. But as you can see, Rollerbot is a much more complicated step function than the ECS instance drainer. It is, I believe, about 20 to 25 steps in the step function that are linked together. Some of the names sort of indicate what they do. For example, we have a validation step. We have ensure that there are no protected instances that can't be terminated. We ensure that we can actually add instances by looking at, I believe it's the Trusted Advisor API to make sure that we're not going to hit a limit. We have, outdated instance counters. We have terminations, and we have recoverable and unrecoverable error handlers that do the right thing. We also have that acquire lock and DynamoDB as well. Some of the things I've learned about with step functions, some of the best practices. So best practice one is surface as much logic in the machine as possible. Don't hide the logic in functions. Keep the functions as simple as possible. Don't branch in them, don't sleep, don't loop. Let the machine do that. Just make your function do as little as possible. So keep them simple. Put the switching logic into choice steps instead. It makes it very clear to the observer what's going on. Notify, as we do, when an execution time exceeds some reasonable threshold. Otherwise, it's possible that a state machine could loop for a year and you might not notice. And then don't bury errors. Surface them as much as you can. At the very least, catch them when possible and notify somebody who might actually be able to take action on them. It's been my experience that my peers really like to. Also, one of the cool things about step functions is the UI. When a step function is actually executing, it has this cool animated display of what step is executing, and when it fails, what step failed. It's been my experience that my colleagues really like to see the various steps, as it makes the logic a lot clearer than diving into the code. And they love to watch those animations too. Again, I just wanted to say Segment has really enjoyed working with AWS on this. We really love step functions. We love ECS. We love Lambda. And I will be I will be available at the Ask a Startup table a little bit later on today. I'd love to answer your questions, talk to you, get to know you. Again, my name is Michael Fischer, and thank you for attending. I really appreciate the turnout and everybody coming to learn about step functions.